Welcome back, soft rock geology fans. We actually make a distinction between hard rock geology, the igneous and metamorphic beasts, and soft rock geology, involving the sedimentary information bombs that we are currently investigating. The soft rocks, the sedimentary rocks, are the best rock type to tell you surface conditions at the time of deposition. When we go to Mars and see layered rock, we know it could be lava flows in some cases, but sedimentary layers in most. Ground truthing robots confirm sedimentary, and even some conglomerate, whose pebble-sized rounded clasts indicate fluid flow of at least a meter per second in meter-deep fluid. Streams on Mars and probably water streams. Hey, they could be liquid CO2 streams up there. So, the size, sorting, roundness, and mineralogy of the detrital material in our clastic sedimentary rocks are clues to us about erosional agents and clastic weathering sources. Water is the most common agent of erosion on Earth, and streams the most common form doing this work. As clastic bedload rolls and bounces along the bottom of a stream, its sharper corners are more easily chipped off, which causes clastic material in a stream to get smaller and smaller the farther it gets from its original source of weathering. It also gets rounder and rounder. So the smaller and rounder clasts are, the farther the distance of erosion. A rock tumbler is a good way to see this process in action and even speed it up by adding a bit of silicon carbide grit. The results of weeks of tumbling around like the bedload of a stream results in overall smaller and rounder clasts. As sediment gets below cobble to pebble or smaller size, the grain has a greater chance of becoming monomineralic, made of one mineral. By identifying the main minerals present in a clastic sedimentary rock, we can get information about the source of those grains. The mineralogy tells us a story, as silicate minerals at the top of the Bowen's reaction series are less chemically stable at the Earth's surface than those at the bottom, and feldspars are only marginally stable. Olivine, pyroxene, amphiboles, what we call the ferromagnesian minerals, all rust away easily at the surface. So a sedimentary deposit or rock that includes these minerals must be fairly close to the source of weathering, as the unstable minerals you're seeing could not have been exposed to the surface of the Earth long enough to break down. This sand comes from the beaches of Hawaii. The source is right there. It's Hawaii. In our rock tumbler, rocks made of the less stable minerals need to be checked, sometimes after just a matter of hours, so they don't wear away completely. Should the ferromagnesian minerals unsurprisingly not be present, because they've all weathered away, or they didn't exist in the source rock at all, but we do see feldspars in our clastic rock. We know we may have gotten a bit farther than the ferromagnesian minerals had, but you're still fairly close to the source of weathering. Feldspars aren't that stable. If you find a sediment completely devoid of ferromagnesians and feldspars, perhaps having only zircons, garnets, or more likely quartz, well, be careful here. Perhaps we sourced this material from a monomineralic source rock nearby, but we can investigate that idea with the context of geology. Look around, see if there's a monomineralic source. But most likely, grains of stable quartz have traveled far from their source. This quartz beach sand in Port Aransas, Texas, was sourced from weathering rock all throughout the Mississippi River drainage basin, including Clear Creek that goes through Golden near my university. This sand shows us another property we can use to get information about the depositional environment: the sorting. This is what we call a well-sorted sand, and the transportation agent of its immediate environment is wind. Wind on Earth can't move clasts much larger than fine to medium sand, and the silts and muds drift out to sea while sand accumulates on higher energy beaches. So wave water sorts the beach sand in that area, and then wind further sorts it to a uniform fine aeolian sand. That is a wind-blown sand. Waves on the beach have a fairly consistent energy, and the wind on the beach has an even more narrow range of energy levels. The more consistent the energy in the environment of deposition, the more consistently sorted the sediment and resultant clastic sedimentary rocks are. Poorly sorted clastic material tells us the energy in the environment fluctuated from high to low. Rockfalls and debris flows result in angular, poorly sorted material. Streams have moderately sorted, rounded clasts as conglomerates or sandstones with interbedded floodplain deposits of well-sorted clay and silt. Glaciers pick up rocks of all sizes and grind some down even to powder, and when they melt, they drop everything at once, resulting in poorly sorted glacial till. We noted earlier that glacial clasts tend to be sub-rounded to sub-angular, with faces that show scours and scrapes. If a glacier drops its poorly sorted mix, but these sediments then get sorted out by wind and or water, the better sorted glacially sourced material is called glacial drift, to distinguish it from the unsorted glacial till. But we must be careful, as glacial drift deposits could be caught up into a landslide or mud flow. And if you ever get a diamictite, that would be the general term for poorly sorted range of glacial clasts supported in a mud matrix. Graded bedding is another way of telling original up direction, but it also tells us there was a high energy event that took a large range of clastic material into suspension, but dropped to a calm condition in a relatively rapid period of time. The largest clasts drop out first, usually rhytic material of pebbles or larger, followed by coarse, medium, then fine sand, then silt, then after days of calm water, the clay comes out. The result is graded bedding, which tells us of this violent event suddenly ending, and which way was up at the time when it was deposited. Graded beds, fine upward. Sedimentary clast size, rounding, sorting, mineralogy, and graded bedding are all called primary sedimentary structures, which are features formed at the time of deposition as opposed to secondary sedimentary structures which form after the sediment deposits, and which we will meet in a couple of episodes. But there are so many important primary sedimentary features that we will need to spend a little more time on them in the next episode, as we meet scraping and scouring tool marks, flute marks, imbrication, ripples, cross-bedding, and rhythmic layers, here on Earth Explorations.